Then it's my great pleasure to introduce you the first speaker of this second session, Bergh from NTNU, who will be speaking about separable equivalences and finitely generated cohomology.
Thank you. And thanks for the invitation to give a talk here. So I'll just give a short report on some work from last year, I think. So this is about what's called separable equivalences and finitely generated cohomology. So let's fix a field which is not necessarily algebraically closed, and two k-algebras such that when you mod out the radical and tensor with itself, you have semi-simple k-algebras. So this is automatic if, for example, the field is algebraically closed or maybe perfect. So we fix two such algebras. Then we say that B separably divides the algebra A if there are bimodules U and V. So these are bimodules over A and B, but sort of opposite bimodules. So U is an AB bimodule and V is a BA bimodule, such that U and V are projective as one-sided modules. So there are four one-sided modules involved here, and all four of them should be projective and finitely generated. So all modules are finitely generated. And B is a summand of V tensor U as a B bimodule. So since V is a left module over B and U is a right module over B, this tensor product is a B bimodule. So that's B separately dividing A. And if the opposite also holds, so that A is a summand of U tensor V, then the algebras are separately equivalent. So for example, if you take a finite group G and a subgroup H, then the group algebra of H separately divides the bigger one. And if you start with a Sylow subgroup, so H is a Sylow subgroup, then the two algebras are separately equivalent. Another example, a trivial example, is if you have Morita equivalent algebras, for instance. So we want to relate the cohomology over such algebras. And we say that an algebra has finitely generated cohomology if the Hochschild cohomology ring, which is the X algebra as a bimodule of the algebra, so the X algebra with the Yoneda product as multiplication, if this is a finitely generated K-algebra, so it's an Noetherian ring. And moreover, whenever you take a one-sided module, say a left module M, the X algebra of that module is finitely generated over the Hochschild cohomology ring. So the X algebra of a one-sided module is always a module over the Hochschild cohomology rings, because there's a ring homomorphism from the Hochschild cohomology ring into the X algebra of M. So it becomes a module. So we require that all these modules, all these X algebra modules, are finitely generated over the Hochschild cohomology ring. And when these two conditions are satisfied, we say that A has finitely generated cohomology. We just write A has FG like this. So there are lots of examples. You take group algebras of finite groups. You can take finite dimensional complete intersections, more generally so-called quantum complete intersections. You can take co-commutative Hopf algebras, and there are several examples of symmetric algebras which have finitely generated cohomology. And the theorem says that if A has FG and B separately divides A, then B also has FG. So in particular, if A and B are separably equivalent, then one has FG and only if the other one has. And let me mention that for this theorem, the symmetric case, so the case where both A and B are symmetric algebras, that was proved by Linkelmann in 2011. So this theorem shows that it holds in full generality then. So let me just give one application if we take a so-called symmetric finite tensor category over a field of characteristic 0, then we can show, or we can give one proof that the cohomology ring is finitely generated, and all these X modules are finitely generated over the cohomology ring. So I won't go into detail here about finite tensor categories or the cohomology ring and such, or the technicalities. So this is conjectured to hold for all finite tensor categories, but using this notion of separable equivalence, we can give one proof for the symmetric case over characteristic 0. And for the proof, it's just a combination of known facts. There's a famous theorem by Deligne saying that such a symmetric finite tensor category over an algebraically closed field of characteristic 0 is actually equivalent to a certain, or the module category of a certain Hopf algebra. And this Hopf algebra is a skew group algebra for a certain group G acting on an exterior algebra. And then a result from 85 by Reiten and Rittmann shows that lambda and the skew group algebra are separably equivalent. And then a result from 2008 by several authors shows that every exterior algebra has FG. So we can use all this to actually, let's say, transfer FG to such symmetric finite tensor categories. So that was it. It was, I don't think I spent all my time at, that's it.
I still have a few minutes, but thank you very much.